So, hey everyone. So, next 25 minutes, I'm going to be talking about KeyValue Tables, which is to Pravega since 0.8. We've added this thing as a top level primitive sibling to streams. And in our view, this is a perfect complement to our streaming workloads. And in this presentation, I'm going to show you why we think it's like that, and also what changes are coming down the pipeline in the upcoming 0.10 release, and what should you expect in the future from us. All right. All right. So first of all, what are KeyValue tables? It's literally a distributed key-value store. They are backed by what we call table segments. A table segment are key-value stores on top of regular Pravega segments, which are the same segments that we use for streaming. It's the same technology used to maintain all of the Pravega metadata. So since version 0.6, all of our scopes, streams, segments, transactions, and now in 0.9 SLTS chunks and everything else you call metadata in Pravega is stored within ourselves via table segments. So what are these table segments? So table segments are pretty much like a hash table abstraction on top of a Pravega segment. So you can do anything. You can insert keys, you can look up keys, you can retrieve, of course, otherwise it will not be very useful. And you can also list keys. So in a nutshell, if I can summarize how they work, all of the updates for table segments, they are appended to the backing segment, which is used as a changelog. The keys are hashed to 16 bytes, and then those hashes are stored in our segment attributes. Segment attributes were introduced a while back to support our exactly one semantics. For stream workloads, we use them to maintain the writer states, but we have since expanded them to be able to support other types of metadata, and currently they are implemented as a B+ tree on top of tier 2 with various levels of caching. So they're also used for other types of metadata, but essentially we can store tens of millions of tiny pieces of information in this thing, which is why we found them as an excellent storage for our table segment index. All right, so a quick summary of the features supported by KeyValue tables. So you can do anything you expect with a hash table. You can do single key insertions, updates, and removals, and they can be conditional or unconditional. What does conditional mean in this case? Every time you insert or update a key, it gets some sort of a server assigned version, which you can view as an E tag. And you get that thing back, and you can get either as part of an update or insertion, or when you get the key. And then if you want to make a conditional operation, such as an update or conditional removal, you have to pass an E tag, and it will only be accepted if your version matches what is currently on the server. Also, you can do multi-key atomic operations. So if you have a batch of, let's say, 5 keys that you want to update at the same time, you can bash them together, and Pravega will ensure that they will either all go in or none of them will. And you can mix and match conditional and unconditional updates within this batch. So for instance, within those 5 updates, you can have 1 or 2 which are conditional and the other ones are unconditional, but the entire batch, the entire update is going to be conditional, those 2 ones. So you can be very creative with what you can do there. Of course, no KeyValue table will be useful if you cannot retrieve the data. So of course, you can go single multi-key retrievals. And then you can also iterate through all the keys and all the entries. And currently in the code that we have out there in 0.8 and 0.9, you can group keys into key families. So one thing which I didn't mention is that KeyValue tables, when you create them, you have to define a number of partitions. Each partition is pretty much a table segment. We do not yet have support for all scanning within KeyValue tables, but that is something we are considering for the future. So right now, when you create this, you have to define a number of partitions up front. And in order to support those multi-key atomic operations, those keys have to essentially be mapped to the same table segment. In 0.8, I mean, which is what we have right now, the way you do this, we have a concept called the key family, and this is what we use for making sure those keys are hashed there. But I put a little star there because with the changes that we're planning to make in 0.10, we're actually gonna retire key families and replace them with something much more useful, and we'll talk about it in a few slides. So a quick summary of the history of KeyValue tables. So we introduced them about 3 years ago in 0.5 when we first made table segments. Next release, we moved all of the segment store and controller metadata to use table segments. And then, so the goal of the initial table segments was to finally produce a public KeyValue table. But we wanted to solve multiple things. That was one of them, but the other one is previously we used to have all of our metadata stored in Zookeeper or scattered throughout our tier 2. And we had various problems with scalability and frequent operations doing that. So we couldn't, so we had to figure out a way. And what better way of doing this than to dogfood it to ourselves. So first we made the table segments, and for 2 or 3 releases, we kept them internal to Pravega to make sure that everything works as planned, and that before we make it available to external users, it's stable and it actually meets the things that we are advocating it does. In 0.8, which was released in September of last year, we published beta 1 of KeyValue tables, which is what we have right now out there. In 0.9, we have released SLTS, and SLTS, the entire chunk metadata is put on KeyValue on internal table segments. You may have heard about a schema registry. The schema registry metadata is also stored in table segments. And now in 0.10, which is what we'll be talking in the next few slides, is the beta 2 of KeyValue tables, which, as you're gonna see, is a big improvement over this. Our goal is that soon after, maybe in release 0.11 or 0.12, we're gonna be having fully supported stable KeyValue tables. All right, so let's go and see what this beta 2 is about. First of all, for beta 1, we have made various performance tests and longevity tests, and we figured out that there are a number of things that have to be changed, that aren't working properly. So we have actually found we've taken a different approach to KeyValue tables, and we've made some major backend changes. I'll detail them in the next slide. The best thing about the beta 2 is now all the KeyValue tables are sorted. So then we will provide order between keys, which will enable additional use cases to be implemented, such as range searches or prefix searches. There will be some minor API changes. Overall, the API stays more or less the same, but we are retiring key families. Why? We'll talk about it in a bit. And the keys are actually broken down into a primary key, which is required, and a secondary key, which is optional. Now, since we retired key families, we've replaced them with the primary key, which is your main thing, and we use that for affinity. Now, secondary keys, you don't have to use them. They're optional, and the reason we have 2 types of keys here is because not all use cases want to have multi-key atomic operations, but those ones who do want to do that, they have to, we can only do it for keys which share the same primary key, which is why we managed to do this breakdown. I have 2 examples coming up, and I'll explain how this can be used in practice. And for the APIs, now we are planning to support iterators for all the keys within the KeyValue tables, courtesy of them being sorted. We're gonna have key ranges and prefixes. So as a structure, each key value table is a collection of table entries. A table entry is literally a key mapped to a value, and it has an e-tag-like version, like I said before. A key is a mandatory primary key and an optional secondary key, where the primary key is just for the partition or segment affinity. For example, let's say we have this simple thing where we have the P stands for primary, S stands for secondary. Suppose you have 3 primary keys where P1 has 2 secondary keys, P2 doesn't have anything, and P3 has one with no secondary key and one with 2 secondary keys. And we have 2 segments, table segment 1 and table segment 2. Now, if P1 hashes to segment 1, pretty much they're going to be mapped to table segment 1. And if P2 and P3 map to table segment 2, then then those other 4 entries will actually be mapped to those segments, and they're going to be recorded in there. So table segment 2 will be the one responsible with all operations for that one. So one thing I want to say is, see here, I use secondary key S1, both for P1 and for P3. Now, you can have the same one. Regard this thing as a namespace. So S1 can exist both in P1 and in P3. They are different keys because internally we put them together, and that's how we create the internal key. So they are different. So let me explain a little bit why we chose to follow this new structure. First of all, we have flexibility in how we encode data. Previously, key families were strings, and so based on feedback that we got from you guys, from our beta users, that is a bit too restrictive. Sometimes you want to just include some random data that makes sense to you, and you have to go out of your way to include it into some string just for us behind the scenes to decode that into a byte buffer and just stash it back. So we've decided to simplify this. So now everything in the key value table is no longer parameterized. Everything is a byte buffer or a byte array, depending on what you want to do. So in that case, it puts the control in the hands of the user. The user can worry about the serialization. So we only have to worry about the actual data within it. So why is this? It's because it's easier to understand ordering between keys. So we've decided to remove the parameterization. So the parameterization is when you get like fancy Java types and you pass a serializer to us, and then we convert that to a bunch of bytes or bits. But if you think about it, numbers are usually encoded using two's complement. Okay, well, they can be encoded like that, or they can be encoded in a different way. So how do you explain to the user what the ordering between keys is? In the backend, we're gonna order keys based on the lexicographic bitwise order. So that means if you see everything as a sequence of bits, it's pretty much like we compare zeros and ones and we put them in the order. So in that case, it's easier for us to explain. If you give us a byte buffer, which is like a sequence of bits, then the order is going to be based on comparing the bit by bit. So it's bitwise lexicographic. And also, giving us byte buffers is easier for us to do prefix or range queries, because all you have to do is give us, okay, here's a sequence of bytes or bits, give me everything we start with this. While if you had parameterized data in with us, it would be hard to say, okay, well, how do you break down a 4-byte integer? What is a prefix for that? So we want to simplify it so we can actually give more power to the user. Let me give you 2 examples now. The first one is our textbook example, the one that usually you see in your university courses. Suppose you have a 2-dimensional table, a multi-column table. You have employee IDs or whatever you want to have in here, and you have columns, which is name, role, and whatever address. In this case, in our case, each row needs to have a unique identifier, and same with the column. We cannot have collisions in there. So how would you store this in a KeyValue table in Pravega? So you have 2 options. Let's look at row format. In the row format, your keys are made up a primary key and secondary key. If the primary key is your row ID and your secondary key is a column ID, then it's trivial how to encode this table in a sparse format. So if you look at the example on the left, in this way, it's very easy to say, okay, give me the entire row or give me a subset of the values within a row. So every row is stored atomically and you can go and iterate to all the rows. But in some cases, you want to have a columnar format. In that case, we swap the order. So first you encode as column and then you put the row IDs. This is pretty much like your favorite vertical format. So in this case, say, okay, I want to get all the values within a column. So give me all the names of the employees or give me all the roles or whatever addresses. You can imagine what kind of creative queries there. Of course, this is not the only way in which you can encode this kind of data. I'm just giving you one example. Developers are very creative and so are you guys. So you just imagine the range of possibilities you can do here. However, Pravega is not really meant to be like a SQL replacement or a NoSQL replacement. Pravega is a streaming storage engine. So let's look at an example where we can marry streaming data with a key value table. So in your typical pipeline, you have event producers. They produce events into an input stream. Then you have your favorite stream processor, whether it's your own homegrown one or whether it's Flink where you put your stuff or whatever you want to do. And then from there, you may have the other downstream components, whether they are specific to your application or may have different stream processors. Well, that's your classical pipeline. But now let's see if you can interject a key value table in there, and then how can you use that thing? And again, let's start with the stream. Let's say that the simple stream is just somewhere to record events pertaining to some sensors. Our sensors measure temperature, pressure, and some rate. I don't know, it's just some generic thing. And each event may have some sort of a timestamp in this example. So let's take this. So the red ones are sensor IDs. We prefix them with the type, which is a temperature. We have PSI and we have rate. And the number after the underscore is pretty much like some unique identifier for that sensor. So we have 2 temperature sensors, 2 pressure sensors, and 2 rate sensors. And they each produce some values, and the timestamps may not necessarily arrive in order because, you know, our favorite network delays and other time drifts, but they're also in there. So let's look at one thing. So first use case. Suppose that we want to get all the values for a sensor type or all the values for a sensor within a time range. In this case, our stream processor can maintain a key value table, which is encoded as sensor ID and timestamp, which points to event values. So if our primary keys are the sensor IDs and the secondaries are timestamp, remember that every key in a key value table now is going to be sorted. So it's very easy to say, okay, give me all the values for a sensor type, which means, okay, suppose I want to get everything for temp 1 or for just for temp, and we can do a range search, so a prefix search, everything that starts with temp. In this case, we're going to get the first 3 entries, and you're going to get all the values. But suppose you have multiple values in there, say, okay, I want to get everything that happened for a particular sensor within a specific time range. So say for temp 1, I want to say everything that happened between time range 500 and 1500. In that case, it's going to return a listing of entries, which is in our example, just the first one. So you can be clear there. Now, let's see what happens if you reverse the order of the keys. So first you make your timestamp as the primary key and the sensor ID as being your second one. Well, this turns a little bit into some sort of a time series database. I'm not advocating that this should be your go-to time series database because, you know, any key value store, any database can be a time series databases, but time series databases are a different domain of their own. I'm just giving an example of how this can work out. So if you use timestamp as a primary key, then look how your data is going to be ordered now. And that enables the different types of queries. So you can use your key value tables and say, get all the values within the time range. So I want to see everything that happened between time 1000 and let's say 1050. And you can do a quick range query, and you can get that. So why would you use a key value table versus just processing your stream? Well, if you process your stream, imagine this, you may have millions or even billions of events. In order to get any sort of query answer from your stream, if you don't have anywhere to index this data, then your only solution is to do a full scan of the stream and find your answer. But KeyValue tables in this case enable you to do interactive queries. So you can, based on your specific application logic, you can say, okay, I'm going to process my stream and I'm going to remember some points which are of interest to me. So that later on, when I need to go access that data, I don't have to go waste my time to scan the entire stream, and I just have to remember those interesting things. So that's one way how we envision the KeyValue tables could be used to complement your streaming environment. Okay, so I'm gonna spend one slide and I'm gonna talk about what is this big backend change that that enables all of these new things in beta 2. So we introduced something called a fixed length key sorted table. So overall, they're vastly simplified compared to existing table segment implementations, simply because we are able to insert the keys directly into our segment attributes. So we don't have to do any hashing or collisions in the backend. So most of the infrastructure that we have for table segments on top of regular segments have to do to resolve collisions and hashing, and that introduces some amount of complexity. However, if we can get a concession from the application that, hey, your keys are always the same length, and those lengths have to be like, let's say, less than 256 bytes, which covers pretty much all of the use cases I've seen so far, then we can offer you a much faster implementation, a simplified one with a smaller footprint and with fewer resources required in order to support your queries. Yes, you will have to be subject to some constraints, like all the primary keys and secondary keys have to be the same length, and your keys have to be less than 256 bytes to begin with. But as an added bonus, you get sorted KeyValue tables, which you did not get before. So in our opinion, this was a worthy trade-off. I looked at the feedback that I got from various people that were trying out the KeyValue tables in beta 1, and I saw pretty much virtual all the use cases can fit within these constraints without any problems. I'm hoping that these changes will not impact whoever was planning to use this in a negative way. I'm hoping that this, on the contrary, I'm hoping that this can actually make this more useful to people. So a little bit about the comparison. Of course, we can, both in beta 1 and beta 2, we can do insertions, removals, updates, conditionals, and multi-key atomics. Yes, we had to reduce the key lengths from 2 kilobytes to up to 256 bytes, but we are providing order between keys, so we are sorted, and now you can list keys, and as an extra bonus, you can do prefix and range queries with a disclaimer that we are not signing up for the last one for 0.10, but it may be done in 0.11 or in a subsequent release, but we are putting that on our roadmap. And if you want more info, we have a dedicated Slack channel in our public Slack. And we have links to the beta 1 design proposal, which includes a lot more technical details than what I was able to present now. And our latest and greatest just out of the oven, PDP-48, which describes the design and the architectural changes, and also the proposed API for beta 2. And you don't have to remember those links. Just go on the Pravega GitHub on the wiki, and we have all the PDPs listed there. Just look for KeyValue tables or PDP-48. So that's it for me. This is the end of my presentation. I see there's a bunch of questions in the chat. So I'm going to open up for like 5 minutes of discussion before we go to Raul.
One of the features that we use a lot from Zookeeper is time to live Z nodes for things like leases. Would you see, so if we use the timestamp as the primary key, could we kind of simulate a time to live node by doing prefix searches in deleting based on the timestamps? Have you thought about kind of that time to live feature replacement?
So actually, that's one of the questions I see on the chat. It's question number 2. So that's actually a great one. So one thing with distributed systems and with distributed storage is that you have to be very careful what you mean by time. So if you leave time on the server side, you pretty much give up some control. So as of right now, we do not have a notion of time baked into our key value tables. So simply because we have the same thing even with streaming. So it's very hard to do anything with time which is actually reliable, which can meet most of the use cases. But if your application encodes time in your keys, like you said, then it could be possible to build a layer on top of the API that we build to implement the time to live support. So we can probably do that.
Yeah. And I think that also kind of relates to one of the other questions from Maxime, which is, range removals. Because if you were searching for a whole bunch of keys in order to manually delete them, then having that ability to delete from a range of primary keys would be really useful.
Yes, that could be done. However, you have to understand we do not have so as opposed from streams where you have distributed transactions, here we do not yet have support for distributed transactions. So that's one of the reasons why we have the restriction that all the multi-key operations have to be on the same primary key because they have to go on the same table segment. So if you want to do a range removal across multiple primary keys, that may actually end up being on multiple table segments. So we cannot guarantee atomicity. So that can be built as a layer within the client, but if the operation fails because something crashes on the client or somewhere else, the operation will only be partially executed. So we'll be able the application to go and handle that, either a partial removal or just resume the operation.
What about within a primary key?
Within a primary key, so since that goes on the same table segment, that can be easily done. It's not in the API, but that can be done as a future enhancement. So let me answer question number 3. Are keys with non-fixed length still support? So the backend implementation exists. We have temporarily removed them for 0.10, and I'm only planning to add them if there is demand for them, because they will have to be added back from the client. But they still exist in the backend, so we still have support. But for those ones, we cannot have them sorted. They will just be like your regular non-sorted hash table. So I'm asking for your feedback. If our users want this, then we are open to doing that post release 0.10. Count of a number of keys in the range. So you can do it by listing the keys. We do not keep statistics for keys within our data store yet.
Hi, Andrei. I had 2 questions about listing. On the previous slide, the changes instead of listing by key family said listed by primary key. Is it required to include a primary key or only if you're doing prefix? Like, can you just get an iterator for all the keys?
All right. So in Beta 2, we have essentially replaced key families with primary key, and we made it more flexible. So from that point of view, there shouldn't be much of a change in there. So you can list all the entries within the primary key. That's already coming in. But the next one, which is the last entry, the prefix range queries and global iterators, yes, we can support them. However, if you look at the footnote number 5, it's not within our scope of release 0.10. It is on our roadmap. We are going to try to do it in 0.10, but it may actually be done in a subsequent release. So yeah, it is in our roadmap, to answer your question.
Okay, yeah, because we're coming from the data's like opaque to us, right? Like we might know the schema of everything, but we wouldn't know the primary keys.
So
and then, yeah.
I'll tell you why that. So while listing by primary key is just a simple delegate to the table segment, which is already built there.
Oh, okay.
Globally, you have to do it distributedly across all the table segments and do a synchronous sort on the client. So that is a bit complex. We have to consider what could go wrong and whatever. So we want to take our time and don't rush it. That's the only reason why we are not signing up for it in 010.
Okay, gotcha. Okay, thank you.
So I'll take one more question because we want to get to Raul before we run out of time. All right, will increasing the number of partitions ever be supported? So maybe. I do have an idea how to do auto scaling, which could include the increased number of partitions. Maybe doing it manually is one way, but there are a number of complications and things that have to be handled there, and we did not sign up for. So we don't want to do it yet in beta in the beta version. But that could be something which can be done if our user community wants it. All right. Well, cool. Well, thank you. Those are some very good questions. Thank you for listening to me, guys. I'm gonna post this PowerPoint presentation on KeyValue Table channel, which is right here in the open Slack. And with this, I'm gonna stop sharing and I'm gonna pass the buck over to Raul.